So, what we have discussed about the fields of an inode, these are the fields which are stored on the secondary storage. Okay. So, following the same logic, why we have come to this inode is that whenever a process puts a request for a particular data from a particular file, the first thing that has to be done is you have to access the inode of the file. Then in the inode, you have to come to the table of content, TOC part of the inode. From the TOC part, depending upon which byte offset of the file is interested in, you have to go to the corresponding data block, maybe either following the direct pointer or single indirect pointer or double indirect pointer or triple indirect pointer. Using some of the pointers, one of the pointers, you have to come to a particular data block, then you have to access that data block. Okay. So for every read operation, for every write operation on the file, you have to access the TOC part of the inode to get the corresponding block identification number. Then once you have the block identification number, then you can check within the buffer whether that particular block is present in the buffer or not. If it is present in the buffer, you don't have any problem. You can simply transfer that from the buffer area to the user area. If it is not present in the buffer, then I have to physically read that particular block from the secondary storage and put it into one of the buffer cache. Okay. Now, because you have to access the inode for every file operation, whether it is read or write, whatever it is, that means once you open a file, it is quite expected that the inode of that file will be accessed a number of times. Okay. Now, for accessing the inode, if every time I have to go to the disk, then obviously the throughput of the file system will be very poor. So, to improve the throughput, what is done is the same concept that we have used for the buffer cache, that is, we put the data block in the buffer cache so that your physical access to the disk, the frequency of physical access to the disk is reduced. Using the same concept, whenever you open a file, the first time you access the inode of that file from the disk and copy that inode into main memory. Okay. So that as long as the file is open, every reference to the file will try to refer to the inode of the file, and now the inode is available in the main memory, so your access time will be quite less. Okay. So this is a copy of the inode in the main memory, which is called an in-core inode. Okay. And the in-core inode is maintained almost in the same way as we have maintained the buffer cache. That is, we will have a free in-core inode list. We will also have a number of hash lists. The hash lists consist of a number of inodes on that particular hash list. Okay. So, to maintain the hash node in the main memory, in addition to these fields, we need a number of additional fields. One of the field is obviously the status field that we have also used in case of buffer cache. So, the first field in the in-core copy, that will be the status field. And as before, the status field will contain similar kind of information. That is, the first information that has to be contained in the status field is whether the inode is locked. Because it may so happen that more than one process opens the same file simultaneously for reading purpose. Okay. In that case, when one process, say P1, wants to read a data from that file, then before reading the data from the file, it has to access the inode to find out what is the block number of the data that is requested. Once it gets that block number, then it can release the inode. Okay. So during this process, the inode should remain locked, so that during the same time, if the second process also wants to access the same inode, it should not be permitted. Once the first process releases the inode, the second process can now access the inode. Okay. So one of the information that you have to maintain in the status field is whether the inode is locked or inode is unlocked. Okay. Here, as we have seen, there is a difference, that as we have seen in the buffer cache, that if the buffer is not locked, that means it is free. But in case of inode, it is not so. Even if the inode is not locked, that does not mean that inode is free. I will come to that later. Okay. So the first information that you have to maintain in the inode is whether the inode is locked. Then the next information that you have to put in the inode is similar to as we have used in case of buffer cache, that whether a process is waiting for this inode to become unlocked or not. Inode to be unlocked. Then other information that you have to maintain is whether the inode is same as the disk copy or there has been some modification in the inode. Okay. So this information is whether inode differs from disk copy, and the other information is, one is inode differs from the disk copy, and the second information that has to be maintained is whether the file data is different or the file data has been modified after the file has been opened. Okay. So here we have to put whether in-core file is different from disk copy. So these are the various informations that you have to maintain in the status field of the in-core copy of the inode. Okay. Then obviously the other informations will be the device number and the device number that contains the file that we are interested in. Okay. Then the inode number itself. You find that in case of disk copy of the inode, we didn't need this inode number, because in that case the position of the data structure in the inode blocks tells you that what is the number of the inode. Okay. So just for example, what we said is that if the inode needs the 50 bytes for representation, if the data structure for inode needs 50 bytes, in that case first 50 bytes in the inode block will belong to the first inode. Next 50 bytes will be for the second inode. Next 50 bytes will be for the third inode, and so on. So it is the position of the data structure in the inode blocks tells you that what is the inode number. But in case of in-core copy, we may not need all the inodes in sequence, and a particular inode may appear anywhere in the hash list or anywhere in the free list. So I need a specific field which will tell me that what is the number of the inode of that in-core copy, whether it is inode number 1 or inode number 2 and so on, which is not needed in case of disk copy. Then obviously I have to have a set of pointers to other in-core inodes, and here again we have two sets of pointers. Okay. One set of pointers will be for the free inode list, and other set of pointers will be for pointers to other inodes in the same hash queue. Okay. Just as we have done in case of buffer cache. And here I have to have an additional field which is not present in case of buffer cache, that is what is called a reference count. And it is the reference count which makes it different from unlocked in case of buffer and unlocked in case of inode. In case of buffer cache, we have said that whenever the buffer is unlocked, that means the buffer is free, and it can be on the free list as well in addition to its existence on the hash queue. In case of inode, because there is a possibility that the same file may be opened simultaneously by more than one process. Okay. And we expect that as long as the file is open, its inode should be present in the main memory. I can remove the inode from the main memory only when the file is closed. Okay. But it may so happen that two processes has opened a particular file. The first process which opened that file first, and because of that file open command, the corresponding inode has been read from the secondary storage, from the inode block, and it has made an in-core copy of the inode. Okay. Now the second process wants to open the same file. So it will get the inode number of the file. Okay. And after getting the inode number, the first operation that will be done is to check the in-core copies of the inodes in the corresponding particular hash queue to see whether the inode already exists in the main memory or not. If it is existing in the main memory, that means some other process had already opened it. So I need not get the same inode from the disk once more because already it is present in the main memory. But what has to be done is this reference count field has to be incremented by 1. Now when the first process closes the file but not the second process, the file is closed for the first process but it is still open for the second process. That means though the first process will not need the data from the file anymore, but the second process will need the data from the file. So first process has unlocked the inode, okay. Maybe the second process has also unlocked the inode because inode will be needed only to get the block address, not for other purpose. Okay. So maybe the inode is unlocked for both the processes, first process and second process, but the second process has not closed the file, but the first process has closed the file. That means file is still open for the second process and the second process is likely to access the data from the same file a number of times. So I cannot simply remove this inode from the in-core copy. I can remove the inode from the in-core copy only when the second process also closes the file. Okay. So that is what is maintained in this reference count field. When the first process opens the file, the inode corresponding to that file is read from the secondary storage and put into main memory, and the reference count field is set to 1. When the second process also tries to open the file, it finds that the inode is already present in the main memory, so it need not be read from the secondary storage. Okay. But now there are two active instances of the same inode. So reference count will be incremented by 1 more. So now reference count becomes equal to 2. So it is the reference count field which indicates that how many active instances of the same file exists in the system. Okay. Now when the first process closes the file, it simply makes the reference count decremented by 1. So earlier reference count field was equal to 2, now it becomes equal to 1. Because it is 1, that indicates the file is still active for some other process. So I cannot simply remove the inode from the main memory, or I cannot put this inode on the free inode list. Because once it goes to free inode list, that indicates that this inode may be overwritten by another inode from the disk. I can put this onto the free inode list only when the reference count field becomes equal to 0. That means there is no other active instance of the same file. Okay. So that can only happen only when the second process also closes the file. So after the first process, if the second process closes the file, then earlier reference count field was equal to 1, now it becomes equal to 0, and when the reference count field becomes equal to 0, it can be put onto the free list. Okay. So that is the difference between your buffer cache management and the inode management. In case of buffer cache, we have said that whenever the buffer is unlocked, I can put it onto the free list. Okay, maybe either head of the free list or at the tail of the free list. But in case of inode, only when the reference count field is equal to 0, even if the inode is unlocked, only when the reference count field is equal to 0, then only I can put onto the free inode list, otherwise I cannot put it onto the free inode list. Okay. Other managements will be almost similar to what we have discussed in case of buffer cache. Right? Now the major operation is, as we have seen, that for getting any data from the inode, I have to access the inode, get the table of contents. From the table of contents, I can get the block number. And once I have the block number, then using that block number, I can check in the buffer cache whether it is present. If it is not present, I have to access that block from the secondary storage, put it into buffer. But what is most important is that we have not said till now is how to know the inode number. Because when I execute a program or I want to open a file, I simply give the file name. Or at best, I can give the path name starting from the root leading to that file. But I never specify the inode number, or even the user need not know what is the inode number. Okay. So there comes the concept of directory. directory plays a very important role in finding out the inode number of a requested file or the inode number of a requested subdirectory. Now, what is a directory? As we said, that directory is a special kind of file. So, just like file, in case of files, we have to have a unique inode. Every file will have to have an unique inode. Similarly, every directory or every subdirectory will have to have an unique inode. Okay. So, I just demarcate between the inode given to a file or an inode given to a directory only through the type field. The type field indicates whether the inode is unallocated. I will not say free, inode is unallocated. That means it has not been allocated to any of the files or any of the directories, or the inode has been allocated to a file, regular file, or the inode has been allocated to a directory, or there are some special kinds of files which are maintained, whether the inode has been allocated to any special kind of file. I will forget about this special kind of file now. Let us consider about only directory, file, and the free inode. Okay. So, whenever a process wants to open a file, usually we give the file name, just the file name if the file exists in the current directory, or we simply give the path name from the root if the file is not in the current directory, or even if it is in the current directory, then also we can specify the path name from the root. Now, what is the directory? As we said, the directory is a special kind of file which contains a list of inode number file subdirectory pair. Okay. So, if you open a directory just like a file, you will find that it will contain two fields. One field is for inode and the other field is for directory or file. Okay. Suppose, so this is the directory of say /etc. Okay. Under /etc, we can have a number of subdirectories or a number of files. For example, under /etc, I can have a directory say bin. This directory bin, subdirectory bin, will have a specific inode number. Let us say inode number 80. Okay. Under this, I can have a file say password. This password again will have an unique inode allocated to it, and suppose this inode is, let us assume any number, say 205. Okay. Now, the sequence which particular inode will be allocated to a particular file or to a particular directory, that depends upon what are the inodes unallocated at the time when this file or this directory has been created. Okay. So, one of the inodes which is still unallocated will be allocated to the newly created file or the newly created directory. Right. So, similarly, it can have many other entries and the corresponding inodes. Okay. So, a directory is nothing but a list of inode directory file pair. Along with this, there may be other attributes just to identify that whether this is a file or this is a directory. Of course, that is also available in this particular inode. So, 80th inode will say that bin is a directory. Similarly, 205th inode will say that password is a file, it is not a directory, and that will be specified in the type field of this particular inode. So, just like this, that when I say that etc is a directory, that etc itself has been allocated a particular inode, a unique inode, which is not allocated to any other file or any other directory. Then along with this, there are two special kind of entries. One entry is dot, the other entry is dot dot. Okay. This entry dot means that it gives you the inode number of the current directory. Okay. Suppose this number is 100. Then as I said that this directory etc, this is the current directory is etc. The directory etc itself is assigned an inode number 100. Okay. Dot dot gives you the inode number of the parent directory of this directory. Okay. So, maybe the parent directory of this has been allocated an inode number of 300. Okay. So find that from a particular directory, using dot, I can find out what is the inode number of the current directory, or using this dot dot, I can find out what is the inode number of its parent directory. For any other entries, whether it is a file or a directory, I can always find out what is the inode number of the corresponding file or the inode number of the corresponding subdirectory under the current directory. Okay. Now, in addition to these directories, there is a root inode, there is a root directory for every file system. Root directory is also assigned an unique inode number. Okay. Suppose the root directory is assigned an inode number, let us say any inode which is not allocated to this 50. Okay. So, for getting the inode number of any file or any directory that is specified, I need one of the two components, either the inode number of the current directory or the inode number of the root directory. Because when you specify a file path, the paths are specified from the root directory itself. Or I simply specify the file name or the file directory which is under the current directory. So, to get the inode number of the target file or the target directory, if I have either the root directory inode number or the current directory inode number, that is sufficient. Okay. The root directory inode number is usually stored in a global variable which is accessible to all the process, but this cannot be modified. Okay. Similarly, current directory inode number is within the directory itself. Okay. So, if I give a command like say open, fopen, syntax may not be correct. Okay. So, if I give a command say fopen password, when presently I am under this directory etc., then how this will be converted to the corresponding inode number. I know that because I have not specified any path name, so this has to be found within current directory only. You simply search the current directory, get the entry corresponding to this file name password, extract what is the inode number of that. Right? So, once I get the inode number of this password, the next operation what is to be done is, you read this inode number. First you check whether this inode number is present in the main memory or not, or whether I have an in-core copy of this inode number 205. If I have an in-core copy of this inode number 205, what I do is I simply increment the reference count field of the in-core copy of inode number 205 by 1. Okay. But if it does not exist in the main memory, if I don't have an in-core copy of this inode number 205, what I have to do is, I have to read the block from the secondary storage which contains this inode number 205. And that is very simple, because in case of inode blocks, all the inodes are put in sequence. The first inode appears first, second inode appears next, third inode appears after that, and so on. So from this inode number, I can always find out that what is the block. If I have more than one blocks containing the inodes, I can always find out that which block contains this inode number 205 and what is the byte offset within the block for this inode number 205. Because I always know that what is the starting block number of the inode blocks, okay? What is the size of every block, what is the size of every inode. All these things are known. So I can always find out that what is the starting byte of this inode number 205 and which particular block, right? So what I do is I simply read that block. For reading the block, again I have to go to that buffer cache management, because this block has to be read and put into the buffer. Then once it is in the buffer, then only I can filter out this inode number 205, right, and get the inode and put this inode into the in-core copy of the inode, right. On the other hand, if the command is given like this, fopen /etc/password, So if I give a command like this, then what I have to do is, because this is a path name starting from the root, I know what is the inode number of the root, because that is stored in a global variable. I have to take out this inode number, read it from the disk, put it into Incore copy. Or maybe while booting, this inode number is already present in the Incore copy. I have to check that this is a directory, not a file, because there are other components on this. So if this is a file, then this path name is not valid. It has to be a directory. So I have to check that this is a directory. On verifying this is a directory, I also have to check that I have the right permission on this directory, that I have to have the search permission on this directory. Okay. In case of directory, search permission is equivalent to execute permission. A file can be executed, but a directory cannot be executed. Okay. So in case of a directory, the search permission is equivalent to execute permission. So if you have execute permission on the directory, then you can search that directory. So if you have the search permission, then what I have to do is, the next component is etc. I have to check that directory. So this etc, this root directory will be some listing like this. I have to search for this component etc in that listing. Once I get an entry for etc, I have to take out the inode number of that. Okay. So once I get inode number of etc, and in this case the inode number of etc is 100. So I have to get inode number 100, again read it from the disk, put that into main memory. Okay. Then from that inode number, I get the disk blocks from the table of content, which contains the data of that directory, and data of the directory is this list. So I have to read this list, then search within this list for this entry password. So I get this entry password, inode number of the password 205. I have to extract this 205. Then on getting this 205 inode in the Incore copy, I can go to the table of contents of this inode. Then once I have access to the table of contents of this inode, I have access to different data blocks containing the data of this file password. Okay. So this is a very, very important step. I mean, always whenever I want to access a file, I want to open a file or close a file, whatever I do, an user process, an application specifies the file name or the path name leading to that file name. It may be file name or even a directory. So first operation that has to be done is, you convert the file name or convert the path name to the target inode number. And that can be performed in this manner. Okay. So once you have access to the inode, you have access to the inode table of contents. Once you have access to the inode table of contents, you have access to the data blocks containing data of that file or containing data of that directory. And data of the directory means simply this listing.
Sir, the parent directory of /etc is the root directory.
Parent directory of
/etc is root directory.
Parent directory of /etc is root directory.
It's inode number.
Oh, I see. So it should be 50. Yeah. Right. It should be 50. For a root directory, the parent directory will be root directory itself. Okay. So now it is clear that given a path name or given a file name, how you can convert that to an inode number. Once you have an inode number, you have access to everything on the file. Right.
That means the second instruction will take more time to execute.
Slightly more time, because this has to be passed. Now, next thing is, so far whatever we have done, we have assumed that an inode is already allocated to a file or inode is already allocated to a directory. The next important question is, how do you allocate the inode to the directory, or how do you allocate inode to the file? For that, what we need to know is, what are the free inodes when the file is created, or when free means unallocated inodes, because free we are using for some other purpose. What are the unallocated inodes in the file system which are not yet given to any other file or any other directory when this new file or the new directory is being created? Okay. So for that, again, the super block plays an important role. In addition to the informations that are maintained in the super block, that we have said that the super block maintains information about the file system itself, that is, how big is the file, how big is the file system, how many files it can store, and all those things. the superblock itself contains a list of unallocated inodes. That may not be an existing list. That is a sublist of the total number of unallocated inodes of the file system. Okay. So in the superblock, we have a list of inodes which are unallocated at a particular instant of time, or a sublist of the inodes which are unallocated at a particular instant of time. Okay. Now let us assume that at a particular instant of time, I have several inodes which are still unallocated on the file system. The inodes may be say 100, 105, 112, like this, maybe inode number 200. Okay, and in this case, this is called a superblock free inode list or unallocated inode list. Okay. So this list is simply the serial number of the inodes. This is not the inode itself, or it is not the data structure, inode data structure. It is simply the serial number of the inode. Okay. To access this inode number 100, I have to go to the inode block, and from the byte offset of this inode number 100, I have to get that inode. That is the data structure of the inode. Okay. Now it says that inode number 100 is not yet allocated to any other file or any other directory. 105 is not yet allocated to any other file or any other directory, and so on. So up to this, inode number 200 is maintained in the superblock free inode list. There may be other inodes free on the file system, but those are not yet maintained in the superblock free inode list. But they will be brought in the superblock free inode list when this superblock free inode list becomes empty. Okay. Now this being the situation, whenever a process puts a request for creating a particular file or creating a particular directory, creation means this is being created for the first time. So it has to be allocated an inode which is not yet allocated. Okay. So what it has to do is, it has to check the superblock free inode list. On checking, it finds that the first inode that appears in the superblock free inode list is inode number 100. That means inode number 100 is not yet allocated to any other process. So this inode number 100 will be allocated to the process or allocated to the file or directory which is being created. On allocating this inode number 100, inode number 100 will be removed from the superblock free inode list. Okay. Now once you allocate this inode number 100, this inode number 100 has to be located on the inode block. Okay. Make an in-core copy of that inode. So far the inode was free, that is type field was set to 0, right. Now the inode is no more free, that means the type field has to be set to either regular file or directory depending upon to which it is being allocated. Reference count has to be made to 1 because file is being open for creation. Okay. And all this updated information of this inode has to be written onto the disk inode. With this, allocation of this inode to the file or to the directory is complete. Then other operations on the file or directory will continue as it is. Okay. Next time another process tries to open a file or a directory, this inode number 105 will be allocated. So that it will continue. Last, when all these entries are empty, the last inode which is maintained in the superblock free inode list is inode number 200. Okay. So when the situation comes that this inode number 200 is to be allocated to the requesting process, then with allocation of this inode number 200, the superblock free inode list becomes empty. Okay. So when it is going to become empty, then what is done is the superblock free inode list is filled up with other free inodes or unallocated inodes on the file system. For that, we have to search for the inodes which are unallocated, and the search operation will start from inode number 201. Okay. So this is an inode, that is the last inode on the superblock free inode list, is called a remembered inode. That means you have to remember this inode number for searching for other unallocated inodes on the file system. Okay. So starting from inode number 201, you search for other unallocated inodes on the file system, and whatever inode number you get sequentially, this search is sequential. You fill up those inode numbers in the superblock free inode list, and finally setting this superblock, this remembered inode in the superblock free inode list. So there can be a situation that suppose the superblock free inode list can contain list of 100 inodes. Okay, and I'm starting my search operation from say inode number 201. There are two situations that I have starting from 201. I have more than 100 inodes free, unallocated, or I have less than 100 inodes unallocated. So filling up of the superblock free inode list will stop when you find that you don't have any other free inode on the superblock free inode list, or the superblock free inode list is filled up. Okay, so at the most I can put 100 inode numbers, or less than that if I don't have sufficient number of inodes which are unallocated on the file system. Okay, so this is the situation. I mean, this is the way in which the inodes will be allocated to different new files or new directories when they are created. Now the reverse process is unallocating a particular inode. How do you unallocate an inode? An inode will be unallocated. You find that inode becoming free whenever you close a file and the reference count becomes 0. But that is not unallocation of an inode. In that case, what you are doing is you are simply removing the inode from the main memory. You won't have an in-core copy of the inode, but the inode is still allocated to the file. An inode has to be made free or unallocated when the file is deleted or the directory is deleted. Okay. So when you delete a file or you delete a directory, in that case, I have to put this one in the superblock free inode list if possible. Okay. So for doing that, what is done is you simply check what is the status of the superblock free inode list. If you find that I have some empty space and empty entry in the superblock free inode list, I can simply write the inode number which is being unallocated into that empty entry. That is one way. If there is no space in the superblock free inode list, empty, then what has to be done is the inode number which is being unallocated, if you find that that inode number is less than the remembered inode, because this remembered inode tells me that from which point I have to search for new inodes, unallocated inodes. Then you replace this remembered inode by this new inode number. Sorry, here the search operation will start from inode number 100 to 100 itself. Okay. So if you find that suppose the new inode which is being unallocated is inode number 55, and at that point I don't have any free space in the superblock free inode list. Okay. So what I'll do is I'll simply replace this 200 by this inode number 55, so that next time I search for free inodes, unallocated inodes, this 55 will be encountered. Okay. Otherwise, if this new inode which is becoming free is more than the remembered inode, then I simply forget it. Don't make any change in the superblock free inode list. Suppose the inode number which is being made free is the inode number 210. This is being unallocated. My earlier remembered inode number is 200. Next time I will start searching from this inode number 200. So 210 will anyway be searched. Okay. So I have, these are the different possibilities whenever an inode is unallocated. That is, if I have an empty space in the superblock free inode list, I simply put this new inode number which is unallocated into that empty space. In case superblock free inode list is full and the inode number that is being unallocated is less than the remembered inode, you replace the remembered inode by this new inode number. If it is more than the remembered inode number, then I don't make any change in the superblock free inode list. I simply mark the inode as unallocated by setting the type field equal to 0 on the disk copy of the inode, so that next time the search operation starts from this remembered inode, that inode will in any case be searched. Okay. So with this, I hope that allocation of an inode or unallocation of inode is clear. Okay. So next day we'll talk about management of disk blocks.